Thank you, Felix, for the introduction. Also, thank you for organizing this great conference. I'm sure it has been a lot of work. So, good. So in this talk, I present a summary of my recent results on coherence distillation in the context of quantum thermodynamics, which can be thought as something analogous to entanglement distillation in the context of entanglement theory. So here in this picture, I've depicted a hypothetical machine for distilling coherence with respect to energy eigenbasis. So in this talk, whenever I talk about coherence, I mean basically coherence with respect to energy eigenbasis. So remember that a density operator rho contains coherence with respect to the energy eigenbasis of Hamiltonian H if rho doesn't commute with H. If it's not, if you can make it diagonal in the eigenbasis of H. And otherwise, if it commutes with H, I would say the state is incoherent. So this hypothetical machine obtains pure states. This denotes pure state here. So it obtains pure states which contain coherence from mixed states which contain coherence with a non-zero rate. And the non-zero rate here is a keyword. And during this process, it can consume an arbitrary amount of work. And the question is whether this hypothetical machine is consistent with the laws of quantum mechanics and thermodynamics or not. So at the end of this talk, I will try to convince you that the answer is no. So interestingly, it turns out that this question is actually equivalent to another question about distilling quantum clocks. Suppose I'm given many copies of a noisy quantum clocks. So the clock is noisy in the sense that it's in a mixed state, but it's approximately synchronized. It's approximately synchronized with the background reference clock here. But I do not have access to this background reference clock, meaning that I don't know what's the current time according to this background reference clock. And then I want to combine these noisy quantum clocks together and find quantum clocks in pure states, which are still synchronized with this background reference clock at a non-zero rate. So the question is whether this transformation is possible at a non-zero rate or not. And again, I will try to convince you that the answer is no. Good. So here is the outline of the rest of my talk. I spent most of my time on just defining the framework and the formalism and presenting a summary of results. I won't have much time to go through the proofs. So I start by basically defining what I mean by distillation machine. I will consider three different definitions and find that interestingly, they are all equivalent to each other. Then I will study the problem of pure state to pure state transformations, where the initial states are also pure, but they are possibly different from the final state. And then I will talk about the process of coherence formation, which is basically the process where you go from pure state to mixed states. So it's basically the reverse of distillation process. And we find that this process of coherence formation gives a new operational interpretation of quantum Fisher information. So I could have just highlighted this aspect of the results. The fact that this coherence formation gives a new quantum Fisher information of a new interpretation of quantum Fisher information. And at the end, I will talk about coherence distillation, both in the IID and single shot regime. Good. So let me start by defining what I mean by quantum clocks. In this talk, for me, quantum clock is any quantum system which has a time-dependent dynamics. So a quantum clock will be described by its density operator rho and its Hamiltonian H. So by definition, the state of clock should be time-dependent, which means that when I just told you that the state is rho, I actually meant a state is rho relative to a particular background reference clock at a particular time t. So for example, at t equal to 0, the state is rho. But at any arbitrary time t, the state will be e to the minus iht rho e to the iht. Now, in this talk, I will also talk about n copies of a clock. So by n copies of a clock with the state rho and Hamiltonian H, I mean a composite system with the tensor product state rho tensor n, and with the Hamiltonian, which is sum of the Hamiltonian of each individual clock. Good. So in the study of clocks, we usually think about systems with periodic dynamics, and that's also the assumption here. So, but in addition to this, I'm going to assume that all these clocks have exactly the same period. So this period tau, which I've denoted here by tau, is just a parameter, it's an arbitrary parameter, but it's fixed throughout this theory. So examples could be just a two-level clock with this Hamiltonian, pi sigma z over tau. I'm assuming h bar equal to 1. Note that whenever you want to think about period is determined by both a state and a Hamiltonian. So it's not enough to say what's the Hamiltonian, I should also tell you what's the state. And in this case, for any state which is not diagonal in the energy eigenbasis, the period will be tau. Another example could be just a harmonic oscillator with frequency tau minus 1. Again, for a generic state, the period will be tau. Good. Now I need a framework to study manipulation of quantum clocks. So naturally, because I'm thinking about performing transformations on quantum system, I'm assuming that, I'm limited to operations, to this kind of operations, completely positive trace preserving maps. But in addition to this, I need to take into account this restriction that I don't have access to this background reference clock. I don't know what's the current time according to this background reference clock. And it turns out, I'm not going to show this here, but it turns out that this kind of restriction can be captured by this kind of covariance conditions. Okay? So let's go through this. I would say an operation ETI is time translation invariant, or TI for short, if it satisfies this equation. If you first apply ETI on an input state and then apply a time translation, you get exactly the same final state as if you first apply the time translation and then apply ETI. And this should be true for all initial state sigma and all time t. Right? Note that here, the input and outputs of ETI could be different, and that's why I'm using H in and H out for input and output Hamiltonian. I'm assuming these Hamiltonians are known and is given to us. We know what are these Hamiltonian, and then if you know the Hamiltonian, then you can check if operation is TI or not. So examples could be, for example, implementing an energy conserving unitary, and a unitary which commutes with the Hamiltonian, it will be a TI operation. Another example could be, which is non-unitary, is preparing system in an incoherent state, a state which is diagonal in the energy eigenbasis. Again, to prepare this kind of a state, you don't need to know what's the current time according to the background reference clock. Good. Now, I have basically defined what I mean by the problem of clock distillation. So you are given these clocks, and then you want to perform an arbitrary TI operation on them and transform them to pure states, basically. So arbitrary TI operation in the sense that an operation which satisfies that covariance condition. Next, I want to think about a different problem, or a problem which may look actually different at the beginning, but it turns out to be equivalent to the problem of clock distillation. And this is the problem of coherence distillation in the context of quantum thermodynamics. So here I want to think of this as a thermal machine which can consume an arbitrary amount of work and can distill coherence with respect to energy eigenbasis. So how can we formalize this problem? Well, one way to formalize this is to use the standard research theory of quantum thermodynamics, or athermality. You have heard a lot about this today, and the notion of thermal operations. So remember, recall the notion of how the notion of thermal operations are defined. So a thermal operation is an operation that I can implement. Sorry, this is very confusing for me. A thermal operation is an operation that you can implement on your system by coupling it to a thermal bus via an energy conserving unitary. So the unitary should commute with the total Hamiltonian, basically. And then it turns out that under this kind of operations, thermal operations, work and energy, or equivalent to free energy, and coherence are two distinct resources. They are resources in the sense that you cannot generate them using thermal operations, and they are distinct in the sense that you cannot transform one to the other. Good. Now the question is, what happens when you give a thermal operation an arbitrary amount of work? So work can be modeled by a system or a battery, which is in an energy eigenstate. And then when you couple this basically to your system by a thermal operation, it's basically equivalent to implementing a unitary which couples your system to your thermal bus and your battery. And the question is, if under this kind of, using this kind of resources, what kind of operations I can do on my system if I give a thermal operation an arbitrary amount of work? It turns out, again, the answer is all TI operations. If you give an arbitrary amount of work to a thermal operation, you can do you can only do TI operations, and you cannot do anything, and you can do all of them. You can perform all TI operations. Good. So, and this follows, by the way, from a result which can be interpreted as an extension of a Stein-Spring dilation theorem, or what I call covariant Stein-Spring dilation theorem. So basically, we find that if we give a thermal machine an arbitrary amount of work, now you find a set of arbitrary TI operations again. Good. Now in this argument, later I'm going to use this framework to study problem of coherence distillation. I prove a theorem like coherence distillation is impossible using TI operations. But in this argument, you may think that I relied on the notion of thermal operations, and I relied on this standard resource theory of quantum thermodynamics. And you may think that if I go beyond this framework, maybe I can do coherence distillation. And I want to argue that this is not actually the case. This argument does not really rely on the resource theory of athermality or quantum thermodynamics. And to understand this, let's try to go beyond this, the notion of thermal operation. Let's think about the most general set of operations that we can do for coherence distillation. What is a minimum requirement for an operation to be called coherence distillation machine? A minimum requirement is that at least the machine itself should not generate coherence, because otherwise you don't know when you look at the output, does this coherence come from the input or is something that is generated by machine? So I want to formalize this intuition. Transformations or operations which do not generate coherence themselves. And one way to formalize this intuition is based on this notion of completely incoherence preserving operations. So the word completely here should remind you how the set of completely positive operations are distinguished from positive operations. So I would say an operation is completely incoherence preserving if it maps incoherent states to incoherent states, even if my system is possibly entangled with another closed system, an ancillary system, which has its own Hamiltonian. If the joint initial state is incoherent with respect to their total Hamiltonian, then their final state should also be incoherent with respect to their total Hamiltonian. So an operation which satisfies this condition for all initial states and all Hamiltonians HA, I would call it completely incoherence preserving. And then, interestingly, it turns out that an operation is completely incoherence preserving if and only if it's TI. See? So basically, I started with this hope that maybe I can go beyond thermal operations. Maybe I can do more. But just this kind of consistency condition forced me to go back to this set of TI operations. If just by considering the set of completely incoherence preserving operations, I again came back to the set of arbitrary TI operations. Good. So to summarize, this is what basically I told you in the last 10 minutes or so. There are three different ways to define a set of operations. A set of TI operation, they can be defined in terms of the notion of invariance under time translation, this kind of covariance conditions. They can be defined in terms of this kind of covariant Stein-Spring dilation, in the sense that you want to perform operation by coupling your system to an energy eigenstate with an energy conserving unitary. And they can be defined in the sense of completely incoherence, using the notion of completely incoherence preserving operations. So these three definitions are basically equivalent. And I think just the fact that there are these different ways to define this set of operations explain why this set of operations appears in many different kind of problems and why they are so useful. Incidentally, the equivalence between these three definitions, here I'm focused on the notion of basically on a specific kind of symmetry, time translation symmetry. But the equivalence between these three kind of definitions holds beyond time translation symmetry. You can define this for any arbitrary group, basically. Good. So from now on, I mean, you can forget everything I have told you so far, and you can just think, and don't forget everything, but Control L. Oops. Oh, thank you. So from now on, you can forget everything I just told you. I was just trying to motivate for looking this set of arbitrary operations. So from now on, I'm basically just focusing on this. I'm assuming that this machine, this box is an arbitrary TI operation, and I'm asking whether some states at the input can be transformed to some states at the input can be transformed to some states at the output or not. Good. So, but let's start with a simpler problem, the problem of pure state to pure state transformation, where the input states are also pure, but they are possibly different from the output state. Now, it turns out that in the IID regime, this problem simplifies a lot. Basically, everything will be determined by a single parameter, which is the energy variance. So, in particular, consider system 1 with the state psi 1 and Hamiltonian H1, and system 2 with the state psi 2 and Hamiltonian H2. And assume they have, as before, assume they have the same period. Remember that in this framework, I'm only thinking about transformation between the systems whose dynamics have exactly the same period. Now, it turns out that the optimal rate of transformation from system 1 to system 2 is given by this basically the ratio of their energy variances. Energy variance for system 1 to energy variance for system 2. More precisely, you can show that for any rate less than this ratio, the transformation from system 1 to system 2 can be done by TI operations with a vanishing error epsilon, where epsilon basically can be error in quantified, for example, in terms of trace distance or fidelity equivalently. And so the statement is that this error vanishes in the limit and goes to infinity. On the other hand, for any rate larger than this ratio, you cannot implement this transformation with a TI operation with a vanishing error, basically. This result is based on an earlier result of Shuk, Versati, and Sirag, and also Gilad Gore and Rob Spiggins. But the proof of convergence in L1 norm or equivalent to fidelity and also the converse bound is established here in this recent paper. Good. So this is a very nice result because it means that in the IID regime, pure state to pure state transformation, the problem simplifies a lot. We have this nice picture that the optimal rate of transformation from system 1 to system 2 is exactly the inverse of the rate of transformation from system 2 to system 1. So to summarize, in the IID regime, all oscillators with the same frequency in pure states are equivalent resources, meaning that by adding or absorbing sufficient amount of energy, their coherence content or equivalent to their information content about time can be converted from one form to another in a reversible fashion. Right? But this also means that if now I think about another system, let's say possibly in a mixed state, and if I find the optimal rate of transformation from this system to this system, then I can also immediately find the optimal rate of transformation from this system to system 2. This is a standard argument in entanglement theory, thermodynamics, and all resource theories. And so I can choose one of these pure states basically as my currency or a standard unit of coherence, and I can quantify the amount of resource in any system by finding the optimal rate of transformation from this system to the pure state. Good. So a convenient choice could be just a two-level system with this Hamiltonian, pi sigma z over tau, and with this state 0 plus 1. This is just my choice. Note that I defined the notion of a standard unit of coherence, or CBIT, for a particular period. So this is a system with that period tau. Now, you can ask, what is the physical relevance of energy variance? See, here we found that the resource content or the coherence content of a system is determined by its energy variance. Why energy variance is such an important quantity? What is its physical meaning? Okay, one way to interpret energy variance is in terms of the notion of quantum Fisher information. So remember the quantum Fisher information for this family of state, the family of time evolved version of rho, basically, for the quantum Fisher information corresponding to parameter t is given by this formula, where here pj and pk are eigenvalues of rho, and psi j and psi k's are the corresponding eigenvectors. Now, quantum Fisher information is the most fundamental quantity in quantum estimation, and it satisfies many important properties, but in particular it's phaseful, meaning that it's zero if and only if a state is incoherent or diagonal in the energy eigenbasis. It's monotone under TI operations, so if I apply ETI, a TI operation on a state rho, its quantum Fisher information cannot increase, and it's also additive for composite systems with tensor product states and with non-interacting Hamiltonians, basically. Good. Incidentally, any function which is monotone under TI operation and vanishes on incoherent states is called a measure of asymmetry. In this case, asymmetry relative to time translation symmetry. Every possible problem. Wait an hour, okay. Okay. Any function which is monotone under TI operation and vanishes on incoherent state is called a measure of asymmetry. In this case, asymmetry relative to time translation symmetry. So quantum Fisher information is a measure of asymmetry. Now, if we go back to our pure state problem, if you look at quantum Fisher information in the case of pure state, it's basically energy variance, right? So this suggests a kind of interpretation of the result that we found before. This says that basically in the asymptotic regime, or in the IID regime, a coherent pure state can be transformed to any other pure coherent state with the same period with any rate which is consistent with the monotonicity of quantum Fisher information. So this is a nice interpretation. But if we want to take this interpretation seriously, it also suggests that when we replace pure state with mixed state, then the rate of transformation should also be given by the ratio of quantum Fisher information. And we will see that actually this conjecture is partially correct. So let's start by the case of pure state to coherence, pure states which contain coherence, the transformation from pure states which contain coherence to mixed states which contain coherence. So this is basically the process of coherence formation. So you can define the notion of coherence cost basically for a state rho. The coherence cost of rho can be defined as the minimum rate of a standard unit of coherence or the CBIT that I need to consume to generate copies of rho with a vanishing error epsilon using only TI operations. So error again is quantified in trace distance or fidelity. And then I prove in this paper that this is the theorem that the coherence cost of rho is basically its quantum Fisher information. Or more precisely, the ratio of quantum Fisher information divided by basically this quantum Fisher information for this standard CBIT. So we see that conjecture that we had, that basically energy variance can be replaced by quantum Fisher information, is correct, at least when we think about transformations from pure state to mixed state. And so this provides basically a new operational interpretation of quantum Fisher information in this context. Good. So next I want to talk about coherence distillation. But before that, let me tell you another interesting property of quantum Fisher information, which I found it very interesting actually. So we saw that for pure state, energy variance quantifies basically the resource content of a state or the coherence content of a state. Now, in the case of mixed state, a very natural quantity to look is the energy variance for purification of this mixed state. So for a given state rho, think about all possible for a given state rho of system S, think about all of its possible purifications with all other closed systems which have their own Hamiltonian. So HA is here the Hamiltonian of the purifying system. And think about all those such purification of rho and all possible Hamiltonians HA of this ancillary system. And ask what is the purification and what's the Hamiltonian HA for which the energy variance is minimized, given that the purification is given that the joint state is a purification of a state rho. And it turns out that the answer is again given by quantum Fisher information. So quantum Fisher information also arises in this kind of single copy problems. Good. Next, I want to think about coherence distillation process, which is the process where I go from mixed state to pure state, many copies of mixed state to many copies of pure states. And I can now define the notion of distillable coherence. For a state rho, I define distillable coherence as the maximum rate of a standard unit of coherence, or the CBIT, that I can distill from rho using only TI operations with a vanishing error epsilon. Right? And so, I mean, that previous conjecture that we had may suggest that this distillable coherence is now again given by quantum Fisher information, but it turns out that that's not the case. In fact, surprisingly, I found that distillable coherence is zero for a generic state. More precisely, if the projector to the support of a state commutes with the system Hamiltonian, then the distillable coherence is zero. Right? So now for a generic state, the generic state has full rank density operator, then the projector to the support of the generic state will be identity, and it's always commute with the Hamiltonian, and so the distillable coherence will be zero for a generic state. So in other words, a thermal machine, even if it consumes an arbitrary amount of work, it cannot distill pure coherence from mixed coherence. And it doesn't matter how much work you spend on this. Good. Now, this suggests that coherence distillation cannot be, you cannot have a non-zero rate of coherence distillation. How much time do I have? Sorry? 7 minutes, good. So, so this suggests that I cannot do coherence distillation. I cannot get a non-zero rate of distillation, but still it might be possible to distill a single copy, or maybe a sublinear copy. So let's think about this problem. It turns out that if you look at, suppose I'm given n copies of a state rho, and I want to use TI operations to distill a single copy of this standard unit of coherence, right? And so the maximization is over all possible TI operations. And the question is, what is the maximum achievable fidelity here? It turns out that for this, you can find an exact formula in terms of H mean, the mean entropy, but the formula doesn't clearly show how this fidelity behaves as a function of n. So to understand this problem better, I looked at a particular example. So suppose I'm given n copies of noisy version of this standard unit of coherence. So each row is a mixture of this phi c bit, the standard unit of coherence defined here, and totally mixed state. Okay, so lambda is just a ratio that mixes them. And so the idea is that I'm given n copies of this, and I want to combine these n copies using a TI operation to obtain a single copy of, basically a single copy of this two-level system, which has a higher fidelity with this 0+1. State, the desired state of unit of coherence, basically. And so the question is, what is the maximum achievable fidelity, right? So I show that there exists a TI operation for which the fidelity satisfies this equation, basically. 1 minus fidelity, or infidelity, is equal to 1 over n. N is the number of copies, times the constant, plus terms which are order 1 over n squared and higher, right? So you see, in the limit n goes to infinity, this basically goes to 0, and you can achieve a perfect single copy of this standard unit of coherence, right? So this shows that even though the rate is 0, if you have given me enough copies of this noisy state, I can distill at least one copy of this standard unit of coherence with arbitrary accuracy. Good. So I don't know if this particular TI operation that they have looked at here is optimal or not, but I know that you can do much better than this. In particular, if you choose the optimal one, you always do your infidelity, or 1 minus fidelity, will be lower bounded by 1 over n times a constant, which is basically, actually the two formulas, as you see, they look very similar. The constant is at most, these two constants are related by a factor which can be as large as 2 at most. So basically, this lower bound is a tight bound. So I want to quickly tell you how this lower bound is obtained, because this also tells, this also gives you an idea about how the proof of the no-go theorem works. How much time I have? 4 minutes. Okay, I can do it. So let me tell you quickly about this notion of purity of coherence, which can be used to show the unreachability of pure coherent states, basically. So I define this quantity, which is called purity of coherence. This pH of rho is defined as trace of rho h rho squared, h rho minus 1 minus trace of rho h squared. So if you think about the spectral decomposition of rho, I can also rewrite it in this way. Here, pj and pk are again eigenvalues of rho, and psi j and psi k's are the corresponding eigenvectors. So this is for the case where this formula works for the case where rho is has full support, or even if this condition is satisfied. But otherwise, I am going to assume that pH of rho is infinite. Okay. So how I have obtained this quantity? This is actually very closely related to Petz-Rayleigh relative entropy for alpha equal to 2. It's actually the second derivative of Petz-Rayleigh relative entropy for alpha equal to 2. And so it turns out that just using this fact that it's related to Petz-Rayleigh relative entropy, you can show that this quantity is similar to QFI, satisfies all these nice properties. This phase Fulming that is 0 if and only if a state is incoherent. It's monotone under TI operations, is additive for composite non-interacting systems with uncorrelated states, and is convex. Despite all these similarities, in the case of pure state, this quantity purity of coherence has a drastically different behavior from quantum Fisher information. It turns out that basically this purity of coherence is always infinite unless the state is an energy eigenstate, in which case it's 0. So in the case of pure state, it's either 0 or infinite. It doesn't look like a very interesting quantity. But comparing this quantity with quantum Fisher information teaches us more about properties of coherence. First of all, here I've just copied the formula again for quantum Fisher information and purity of coherence. First of all, you can show that purity of coherence is always larger than or equal to quantum Fisher information. Then, in the case of qubits, you can actually calculate this, and you can show that quantum Fisher information is, purity of coherence is quantum Fisher information divided by 2 times 1 minus trace of rho squared. And this means that just working with this formula, it means that as your state is getting closer and closer to the totally mixed state, the denominator goes to 1, and purity of coherence becomes almost equal to the quantum Fisher information. In the opposite limit, on the other hand, as your state becomes more and more pure, this basically, the denominator vanishes and purity of coherence diverges. So it turns out that this kind of relation actually holds in more generally. So for any general system beyond even qubits, the ratio of purity of coherence and quantum efficient information is approximately 1 when rho is epsilon close to the totally mixed state. And in the opposite limit, when the state is close to a pure state, then purity of coherence diverges as something like similar to this. So the intuition that I want to give you here, I don't want to go through all these formulas, but the intuition is that purity of coherence, roughly speaking, can be thought as something like quantum efficient information divided by 1 minus purity. And so it basically sees the difference between pure coherence and mixed coherence. So in some sense, quantum efficient information doesn't care about this difference, but purity of coherence sees this difference. And this is actually the reason that it turns out to be a very powerful tool to study this process of distillation. So, for example, the bond that I showed you before, it just follows from, which was a tight bond, it just follows from this monotonicity of purity of coherence and its additivity. And also the proof of the result that why the distillation process doesn't work. I'm not going through this proof, but it follows from combining the behaviors of quantum efficient information and this quantity that I call purity of coherence. Good. So here is the summary of my talk. I basically started by justifying why I'm interested in this set of TI operations or operations which satisfy this kind of covariance condition. We saw 3 possible definitions, which comes from 3 possible intuition that you might have about the distillation process, and you find that they are actually all equivalent. Then we discuss about operational interpretation of quantum efficient information in the context of coherence formation, where you go from pure state to mixed state. And at the end, I will talk about distillation process. We find that in general, for a full rank state, the distillation rate is 0, but still you can distill a single copy or sublinear copies of pure coherent states. Thank you for your attention.
Thanks, Lodiman, and very sorry for the laptop. There's a question. 2 questions.
Hello. Yeah. Sure. So you've taken as your unit for distillation the plus state, but you could equally depolarize the plus state. And if you depolarize it to the maximum unit state and use that as your target for distillation, you'd have an infinite rate of distillation. So do you have any idea about how much you would have to depolarize the plus state in order to have a finite
So you mean if I wanted to distill a mixed state, if my standard unit was a mixed state? I haven't looked at that, but I mean, I expect that in that case, I'm pretty sure you can get a non-zero rate, basically, in that case, if your unit was mixed state itself. Question?
So in most of the resource theories, we see entropy or relative entropy arise as the rates of conversion. Right. And so given that, I'm just trying to understand a bit more why the variance appears. I know you had some explanations, but if you could just say a bit more about that.
Well, first of all, you know that the regularized relative entropy in this case is 0, right? So, and the intuition is this. I mean, this is my intuition. I don't know if it's clear or not. So here, you should think of this as a problem of sampling from the same. So think about this classical problem. I start sampling from a probability distribution, which is, let's say, which may be shifted by an unknown shift. I don't know that shift. And so the question is that each new sample that you give me, how much information I obtain. So in this context, then if you think about the classical problem, you also see that you shouldn't expect a linear increase in relative entropy quantities.
I'm just wondering that I would imagine there's some obvious or at least reasonable connections to error correction, quantum error correction here. Do you have any thoughts on that?
I don't have, but that's a very good question. I don't have. There might be a connection to this, the no-go theorems that people look at. Sepper has looked at this problem. Philip has looked at this problem. So there might be some connections. I couldn't establish something rigorous about this connection, but that's a very good question, I think.
More questions? I have one.
Sure, please.
So is entanglement distillation still possible?
Entanglement distillation?
Yeah, I mean, like there's a connection between coherence theory and entanglement theory, right?
Yeah, I think that's a different version of coherence theory that you're talking about. That's coherence theory defined based on the notion of incoherent operations which map, And so
this framework doesn't apply here, really.
Well, this is the set of free operations in that resource theory is different from this resource theory, right? This is here the set of TI operations is, comes from quantum thermodynamics or lack of reference clock or something like that. That's a different resource theory of coherence, which have, I assume, have other, you can find other motivations for the set of incoherent operations. But it will be a very different problem.
And the other one is a superset of this, or are they incomparable?
Comparison between the two theories is a little bit hard. So if you look at a single system, then, okay, let's say I have think about a single system with energy eigenbases, then a transformation which only just permute different energy eigenstates, it will be a free transformation in that resource theory, but it's not a free transformation in this resource theory. On the other hand, if you think about composite systems, then an entangling operation can be free in this resource theory, but it won't be free in that resource theory. So there are some fundamental differences. Right.
Any more questions? If not, let's thank Iman, Philip, and Ralph again.